Hello, Happy New Year and welcome to 2008. We've got two shows for you this week, a second edition of our newly launched podcast, Ask the Naked Scientists, and a 2007 30-minute climate change special, in which we'll look back over the last 12 months at some of the key global warming stories that we've been covering. So sit back and enjoy. First up, here's Dave Ansell, Sue Marchant and me getting together to Ask the Naked Scientists.
Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
I'm pleased to welcome into the studio live here tonight the lovely Dr. Dave.
Good evening.
How are you?
I'm good.
Good. Got loads of questions coming up here as well. I'm going to start with one from Mundo Pace, who says, what happens if you are travelling at the speed of light, then turn your headlights on?
First thing is, you couldn't actually be travelling at the speed of light. So imagine relative to us, you were going at maybe 99.999% of the speed of light, so almost there. If we looked at you and you turned your headlights on, it would look like the light coming out of the headlights was going just very slightly faster than you were. But if you looked, it would look like it was going away from you at the speed of light. Because the really strange thing about the way the universe seems to work is that everything changes in order to keep the speed of light constant. Your time will change and your space will change in order to make you think that the speed of light is still going at the speed of light. So all sorts of the time and space will warp and change shape in order to make the speed of light go at the same speed. But the speed of light is always constant. So if we look at you, it'll be going at the speed of light. Look at the light, it'll go at the speed of light. Or if you look at it, it'll be going at the speed of the light. Just everything else will change in order to let that happen. It sounds absolutely crazy, but it is the way the world seems to work, or the universe seems to work.
Ah, okay. All right, so the universe is changing it.
Well, I mean, it all works, and the universe doesn't really change. It just depends how you look at it. It can look very different. If you look at it when you're moving, it will look very different to how if you're not moving.
Right, okay, Mundo from Norwich. I hope that makes some sense for you. There's another one here, which is coming from Steve by email, and he says, if matter can neither be made or destroyed, where did it come from in the first place?
That's one of the big questions where everything came from. Matter can't quite not be made or destroyed. It can get turned into energy, and energy can get turned into matter. So if you have an electron and you get something called an anti-electron, which is another type of matter, and the two hit each other, then they produce a load of energy and the matter disappears. But if you consider mass as a matter and energy was all the same thing, where that came from, we don't really know. It's something which happened at the very beginning of the universe, and it's so far back that we don't know, fundamentally.
All right, because Steve goes on to say, does that mean that we are made up of atoms that are as old or even older than the universe itself?
The atoms themselves can get changed. I mean, in a nuclear reactor, you split atoms, so you take one atom and change it into a different set of atoms. And in fact, all of the atoms which are made up of, apart from the hydrogen, most of them will be made in stars, or actually start exploding stars, supernovae. Any metals heavier than iron were made in supernovae. So the atoms can have got rearranged, but the particles making them up and the energy that made up the atoms has been there since the beginning of the universe.
Well, thank you very much, Sir Stephen. Thank you very much, Dr. Dave. And I'm pleased to say we have the lovely Dr. Chris. How are you?
Hey, I'm good. How are you?
Yeah, fabulous. Now then, about the blue tongue plague, John says, how is it possible that we can blame a minute continental midge for the blue tongue plague?
Well, let me ask you another question. How many people do you think catch malaria every year?
Oh, gosh. I don't know. I know the statistics are quite phenomenal, aren't they?
There's about 300 million people every year, and about
Crikey.
1% of them will die, so that's 3 million deaths a year. Now, that's in human terms,
Yeah.
and that's malaria. And, of course, the thing that spreads that is something not that different to a midge. It's a mosquito, a blood-sucking insect. So these insects are, in fact, the most dangerous animals in the whole world. If you ask people what's the most dangerous animal in the world, they invariably say sharks and poisonous spiders and snakes and things. But actually, on a weight-for-weight basis, in terms of the number of corpses, if you stack them all up, time and again, it's always the mosquito, because it spreads malaria and it spreads dengue and it spreads a number of other infections which kill people on a huge scale. So to me, the finding that midges spread blue tongue around is not that amazing, because malaria just makes the whole thing pale into insignificance, Sue.
Yeah, absolutely. As far as symptoms are concerned, what should people be looking out for? Because we say, malaria and that kind of thing. So what should we be looking out for?
It's mainly a fever, and the thing that we say in medicine is the fever in the returning traveller, someone who's been to an area where we know there is malaria, and then they come home, and the right amount of time later, they develop a fever, and the shivers and the shakes, and then you take some blood from them, and the way we diagnose malaria is intriguing. You put some blood on a glass microscope slide and squidge it underneath a cover slip, so you make a sort of thin film of the blood, and put it under a microscope, and you look for the parasite in the red blood cells, because malaria is a parasite, so Plasmodium is the name of it, and you can see them inside red cells, because part of the reason malaria spreads in blood is because it homes in on our red blood cells, gets inside them, and then grows in there. And that's why it's transmitted in blood, because when a mosquito comes along and drinks the blood, it sucks up some of the malarial parasites with the blood that it's eating to feed itself.
Ugh. Horrible things. Right, let's go from blood to oil. June has sent a text in to say, when was the biggest oil spillage in Wales, and how many tonnes of oil was it, and where in Wales did it happen?
I didn't know there'd been a huge Welsh oil spill that had made kind of international headlines. I mean, there have been lots of oil spills around the world, and they're always devastating because you end up with literally 250,000 tonnes of crude oil washing up on a beach. And crude oil's horrible stuff. If no one's ever seen it, it's very thick, viscid, sticky, and of course it repels water, so it clings to itself and other oily things, and birds get into all kinds of terrible problems because it sticks to their feathers. It stops the oxygen reaching the water, so it can cause the water to stagnate underneath, and this can cause problems for wildlife. And because crude oil is full of other nasty chemicals and carcinogens, it's a major health risk, so it's bad if it does get out. But I'm not aware of Wales having a massive disaster, but then I'm not very up on the Welsh oil industry, and maybe someone could put me in the right direction.
Mm-hmm.
Apparently there was a fairly large oil spill from the Sea Empress oil tanker in near Milford Haven, because Milford Haven's where all the big oil tankers, they can't get up the channel because it's not deep enough.
Sure.
So they empty some of the oil out at Milford Haven, and it moves around the UK in pipes, and they go up to Rotterdam to empty the rest of it. Apparently a big supertanker called the Sea Empress went aground and spilled maybe 65 or 70,000 tonnes of oil.
Ouch.
In the late 1990s, I think, 1996. So I'm guessing that's the biggest one. I haven't heard of another one.
No, OK, thanks for that. June also asks, how can you tell how polluted the air in your area is?
The best bet that I've found, having a quick look on the internet, as you do, is there's a thing called the UK Air Quality Archive at www.airquality.co.uk, and that's got a list of... There's a whole lot of air quality monitoring stations in the country. There's one of them in central Cambridge. There's mostly they're in the centre of towns. There's a couple of them out of the towns. Yeah. And you can find a list of what the automated instruments were reading today, and there's an archive over the last few years as well. So I'd have a look at that, although if you don't live in the centre of a town, it probably won't help you an enormous amount.
What was that website again?
www.airquality.co.uk.
Airquality.co.uk. Thank you.
It's run by the government.
I've learnt something now. Now, here's an interesting one. Mandy in Lakenheath asks, if the black box in a plane always survives a crash, why isn't the rest of the plane made of the same material?
Unfortunately, you could make the plane out of the same material, but the people wouldn't be made of the same material, and the people decelerating very, very fast is what kills people in plane crashes. It's the sudden trauma. You're going from hundreds of miles an hour to a standstill in less than a second. And unfortunately, your body isn't made of that material that can withstand this and bounce back elastically.
Yeah, the other thing is that even if you did make a plane out of the same material, it almost certainly wouldn't survive. Because if you imagine something like a match, and especially if you're trying to compress something, and most accidents are when things crash and compress. If you imagine compressing a match, trying to squash it between your two fingers, your fingers would probably die before you'd hurt yourself far too much. You wouldn't be able to crush it long ways just between two fingers. But if you imagine something made out of the same material, but maybe sort of a metre long, it'd be very, very easy to break it. Because if something gets longer, it gets much more flexible, and it actually gets harder to make something strong. So a plane, to make it strong enough to survive, to make it as strong as the box, would be almost impossible on the scale of a plane. And it would be incredibly heavy if you did do that. And also, the bigger you get, the more the forces are when you crash into something. So you've got more energy to dissipate. And so there's a thing that I remember hearing, that if you drop a spider down the well, it just goes down the bottom, it walks away. You drop a rat down the well, it'll fall down, it might break a leg. A cat might break a leg. You drop a human down the well, they'll probably die. But if you drop a cow down the well, it'll actually go splat.
Interesting thing I can add to this, Dave, actually, scientists have proved, no animal rights people phone me up, please, but if you drop a cat out of about a 4th floor window, it's more likely to die than if you drop it from a 9th floor window. And they've done experiments showing why this is. When you drop the cat from the window closer to the ground, the cat kind of panics and thinks, oh God, I'm dropping, and it tenses up its muscles. And when it lands, of course, all of the energy of its fall gets exerted right the way through its stiff legs and its stiff body with all its muscles contracted and tensed. And this is very bad for the cat's anatomy. But when you drop it from a much greater height, the cat panics initially, realises it's falling, thinks, oh well, and then relaxes again. No one knows exactly why, but it relaxes again. And then when it slams into the ground, even though it's probably going a little bit faster, but not much, because it's reached terminal velocity, probably from the lower floor anyway, it hits the ground, and because its muscles are all relaxed, they act like giant elastic springs, and they soak up a lot of the energy, and its rib cage hits the ground as well, and this wins the cat a bit, but it soaks up some of the energy, and the effect is to decelerate the cat more slowly than if it just lands on rigid feet, and it's much more likely to walk away. At least that's what science says, and it's been proven.
Oh, how scary is that? I mean, there have been some people who've, thrown themselves off of buildings and things a long way up and survived, haven't they, or fallen because it's been a long way down and obviously the same principle.
Well, I think cats are slightly better because having 4 legs, they're actually distributing the force over 4 limbs, not our 2. So if you drop straight down, you're distributing all of the energy straight through both of your legs. If you land flat and you land on your rib cage, yes, you'll probably break a lot of bones, but you can dissipate the energy because you're spreading the area of your body that's taking the force of decelerating you, the earth pushing you back in the opposite direction. It's spread over a much bigger area, and therefore the actual amount of energy going through each bit of your body is lower, and therefore you're less likely to get as bashed up as if you drop straight vertically. I was aware of someone that tried to kill themselves by jumping off a bridge. They jumped off a bridge onto a road that had been freshly resurfaced, and they hit the road, and it was sort of tarmacky stuff, a bit soft, and their feet broke off sideways and their leg bones dug into the road surface. Not very pleasant, and they had to be sort of carefully removed and then put back together in hospital, and I think they survived, actually. It was very lucky.
Crikey. Ken of Hockley has a question. He says 2 related questions. Can you transplant a heart after a heart attack, and can all transplants be put into the opposite sex?
Oh, the answer to that's definitely true. Yes, Ken, good question. A heart attack is when blood flow to the heart is interrupted, and the heart has its own blood supply. It's got coronary arteries which come off of your main blood vessel, the aorta, and they run around the outside of the heart, giving off little branches that supply the muscle. And if those branches become blocked, usually because there's a deposit of what's called atheroma in the wall of the artery, then the blood flow ceases to that bit of the muscle. And because the heart is so active, it burns off huge amounts of energy and oxygen every given second. And if you deprive it of its blood supply for any fraction of time, you can begin to kill the muscle cells. But you can have a very mild heart attack. You can have a small interruption to the blood flow, and it'll leave the heart largely intact without too much damage. And so there's no reason why, if you were desperate, you couldn't transplant a heart. Say you had a twin, your heart clapped out, and your twin was, say, killed in an accident. There would be no reason, if your twin had an otherwise healthy heart but may have had a heart attack in the past, there'd be no reason why you couldn't transplant the twin's heart into you. And the idea of using an identical twin is that you'd be genetically compatible and there'd be no problem with rejection. In terms of the difference between the sexes, there's no reason why you can't move a lady's organ to a man or a man's organ to a lady. The main constraints are they genetically compatible? And we're looking at how the immune system recognises things rather than sex, because the immune system isn't sexist. It doesn't care what sex you are. It's just more interested in how different you are. Mm-hmm. And the other point is that men's organs tend to be a bit bigger than women's organs, so you also have to factor that in. If you've got a massive, great, strapping guy and he's going to give a liver to a lady who's very petite and small, there might be a problem of size. So you also have to account for making the organ fit. But in general, no, there's no reason why you couldn't transplant a man's and a woman's organs from one to the other.
Thank you very much. Martin has sent a text in from Harwich and says, Sue, you're bonkers. Thank you very much, but we still love you. Can I ask the good doctor, what is the cause of acid reflux and is there a cure? Acid
reflux, also known as gastroesophageal reflux, Martin, is where The acid that's made in your stomach is hydrochloric acid. You have specialised cells that line the stomach, and they're called oxyntic or parietal cells. And what they do is exchange ions of one chemical called potassium for a second chemical, which is called hydrogen. And they pump out these hydrogen ions, and they're the acid, into the stomach. And the stomach is specially geared up to protect itself from this acid. So there's a layer of slime or mucus on the surface lining of the stomach, which stops the acid getting at the wall of the stomach. The cells that line the stomach also grow very fast, so they can replace any cells that get worn away. And as soon as the stomach acid leaves the stomach to go into the small intestine, the juices that come out of your pancreas and out of your gallbladder are very alkaline, and this neutralises the acid and stops it damaging the small intestine. But the pipe that carries food from your mouth down into your stomach, the esophagus, doesn't have the same degree of protection because food's only supposed to go one way in the esophagus, from your mouth into your tummy. And there's a valve at the bottom of the esophagus called the cardiac sphincter. And normally the muscle there clenches down tightly and holds this tissue together so that stuff in the stomach can't come back the wrong way. But there are a number of conditions. One of them is called a hiatus hernia, which is where you get a relaxing effect of this sphincter, and some of the acid can bubble up into the esophagus. Mm-hmm. And because the esophagus doesn't have the protection that the stomach lining does to ward off the acid attack, it irritates the lining of the esophagus and burns, and it produces this unpleasant sensation of rising burning and heat and pain going up the middle of your body, sometimes even into the back of the throat. It's very uncomfortable. And if it's allowed to continue for a long time, it can cause ulceration in the esophagus, it can cause scarring and stricturing, so it's hard to swallow things, and it can also lead to cancer. So it's worth making sure that this doesn't go on for a very, very long time, because it can cause this condition called Barrett's esophagus. The way to ward this off is to reduce the amount of acid in the stomach. And the way in which doctors go about that is by giving a family of drugs. And there's a whole lot of drugs that are out there now that are really good with very few side effects. And one of those is a drug called omeprazole, which is one of the first ones. And it locks onto those cells I mentioned earlier, the parietal cells or the oxyntic cells, and it inhibits the enzyme that makes those acid ions go out into the stomach. So it stops the stomach wall producing acid. And if you cut down the amount of acid in the stomach, this reduces the reflux. You can also do clever things to reduce the hiatus hernia that some people have, and you can also do something where you wrap some of the top of the stomach around the base of the esophagus with an operation called a Nissen fundoplication, and this also reduces the amount of acid bubbling up. But people try and use drugs rather than have an operation if they can.
Sure, and of course diet can help, can it?
Well, being a bit on the large side, having a lot of pressure around your middle can encourage esophageal reflux. So if you lose weight, that does seem to be better. And also smoking increases the stomach acidity, and you're more likely to have acid bubbling up if you smoke. So if you can kick the habit, that will also help to reduce the problem.
Anne says she recently heard that a person can live off baked beans alone. Is this true? And can you elaborate on it? I think Dave's probably a living testament to living on baked beans alone, are you?
I've never done even that much baked beans. There was a Czech guy in my undergraduate who lived off virtually nothing but baked beans and bread. But I don't know what's in baked beans. I guess there's
beans is in
carbohydrate
beans in
and
there, Dave.
Protein. Yeah, I mean, as in sort of nutritionally, Chris.
Some tomato. Beans have got a lot of fibre, and this is what frustrates the bacteria in your guts when you eat them, which is why beans are so what are called fartogenic. They make you fart. Although men much just the same as women, so there's no sexism here. I think that beans are pretty good as a balanced source of materials in your diet. They've got vitamin C because they've got tomatoes. They've got some B vitamins because of the tomato juice. They have got soluble fibre, which is good for keeping you going regularly and keeping everything happy and hunky-dory. And they've also got complex carbohydrates, which are a useful long-term store of energy because the body has to chew the carbohydrates up before they turn into sugars, which you can then absorb and burn in your body. And for this reason, they tend to fill you up for quite a long time because it takes time to break the beans down, and then you absorb the goodies, and then you get the benefit. So they're a good sort of long-term fuel source. I'm probably pushing up Heinz's share price here by fortunes, I should think.
Well, I wouldn't recommend doing it deliberately unless you're in a dire straits, because it's always best to have a bit of a varied diet, I feel.
Right, OK, let's get on with another question here, because we've only got 3 minutes left. Peter says, if you have a head-on collision at, say, 50 miles per hour with another vehicle doing 50 miles per hour, you would think the speed you would be thrown at would be 100 miles per hour, but it's actually 400 miles per hour. Why is this?
I think there's various things going on here. First thing, if you drive into a wall at 50 miles an hour, say that does a certain amount of damage. If you drive at another car doing 50 miles an hour, that's the same weight as you, then in fact you'll both just stop exactly the same as if you'd hit a wall. So it's exactly the same as driving into a wall at 50 miles an hour. If you drove into a lorry doing 50 miles an hour and you were doing 50 miles an hour, you'd start off going 50 miles an hour forwards. You'd end up doing 50 miles an hour backwards. So it's a bit like having a crash at 100 miles an hour. Now, the energy that something has is proportional to the square of its speed, so the speed times the speed. So if you double the speed, the amount of energy goes up by 4. So if you drive into an articulated lorry at 50 miles an hour, the amount of energy, it would be as if you crashed into a wall with 4 times as much energy at 100 miles an hour. I think that's what he's thinking about.
OK, so why is that? Is it just...
Because, energy, if you think about it, it's a force times a distance. So if something's going faster, you've got to apply the same force the same amount of time, but it's gone for more distance. So the faster you go, the more, if you're going at 50 miles an hour, adding 1 mile an hour energy is a lot more than if you're doing 20 miles an hour, because you're already going faster.
Thanks, Dave. So that is Ask the Naked Scientists. And if you'd like to subscribe to that podcast, the details are all on our website. That's nakedscientist.com/ask. And it'll now be coming out every Friday, but it is on a separate RSS feed, which you'll need to subscribe to if you want to carry on getting copies of it, because we return to the normal Naked Scientist programming from next week. In fact, this week coming, we're going to be looking at the science of addiction. So if your New Year's resolutions include kicking certain habits, then we may just have the answer for you. You can send any questions to chris@thenakedscientist.com. Where do you stand on the issue of climate change? Do you think it's real, or a scientific theory seriously lacking substance? And whether it's true or not, what are the alternatives to burning coal or oil to heat homes and power cars? Well, this week, I'm going to take a look at the science behind global warming and also find out about some of the consequences that climate change could have in store for us. But first, what's the evidence that things are actually warming up? Well, ironically, the best place to look is the coldest place on Earth, and that's in Antarctica, where Eric Wolf has been examining samples of ice for clues to what's happened to the Earth's climate over the past 800,000 years.
The Antarctic ice sheet is up to about 3 miles thick or 4.5 kilometres thick at its thickest part. And if you drill into it, you're effectively drilling through snowfalls that go back over years, actually over hundreds of thousands of years. And the oldest core that we've worked on now is 800,000 years old. So we drill out this cylinder of ice, so 10 centimetre in diameter, but 3 kilometres long.
Do you do it in an environmentally friendly way?
We do it in a as environmentally friendly a way as possible, but I'm afraid there's no getting away from the fact that going to the Antarctic is not actually an environmentally friendly thing to do by itself, but hopefully you'll think the benefit was worth it. So we drill this cylinder of ice, and in the ice there's lots of evidence about what the climate was like in the past, how much snowfall there was in the past, what the temperature was, and perhaps most crucially, we have these little bubbles in the ice because the snow compacts to form solid ice with air bubbles trapped in it. You can then crack open these bubbles again, put them into a chemical analyzer and find out literally what the proportion of carbon dioxide to nitrogen and oxygen and all the other parts of the air.
So it's like a time capsule going back over hundreds of thousands of years. How far back can you wind that clock?
So far we've gone back 800,000 years. We think there is older ice around in the Antarctic, and we'd like to get to the older ice, but that's as far as we've got so far.
And what do those 800,000 years tell you?
Well, in that 800,000 years, we know that the Earth's gone through roughly 8 ice ages, ice age cycles. So what I mean by an ice age is when there's ice covering Northern Europe and North America. In Britain, it's as far south as Norfolk at times, or even a little bit further. It also happens that it was colder over the whole of the globe, including the Antarctic. And what we've also found is that every time it was colder, there was less carbon dioxide in the atmosphere. Every time it was a little bit warmer, like it has been for the last 10,000 years, there's a bit more carbon dioxide in the atmosphere, but never anything like the amount that there has been in the last few decades.
How much has it changed?
Well, let me just give you some I guess some numbers first. In the last 800,000 years, carbon dioxide's always ranged between 180 parts per million, so that means of every million molecules in the atmosphere, 180 are carbon dioxide. It's ranged between 180 in the cold periods up to 300 in the very warmest parts of the interglacials like we're in now. But at the moment, it's 380 parts per million, so that's already 30% higher than it's ever been. And there's only one possible explanation for that it's human activity. We do have other evidence for why it is. We can look at the isotopic composition of the carbon, and that looks like stuff that comes from fossil fuel rather than from natural systems. And we just know how much material we're putting into the atmosphere. You can calculate it, and it works that's contributing to the increase.
But at the same time, whilst you can demonstrate there's lots of carbon dioxide in the atmosphere, it doesn't actually tell you that that's the thing that causes the warming, though, does it? Because there are other things that can be more of a greenhouse-provoking agent than carbon dioxide. Take water. Water's much more of a heat reflectant than carbon dioxide, isn't it? It keeps us warmer than carbon dioxide does. Methane, too.
Absolutely. The biggest greenhouse gas is water vapour, but of course we don't have any control over water vapour, so the water vapour just acts as a feedback in this system. It's the carbon dioxide that we can actually do something about. Methane as well, but methane, although it's more effective, is at lower concentration. But that's also double now the concentration that it was any time in the last 650,000 years. So there's no comfort to be had from talking about other gases like that. So the carbon dioxide is increasing very fast, actually about 50 times faster than any time we can see in the historical record. But you're right to ask, how do we know that that's causing the change? We can see that every time in the past when we came out of an ice age, the CO2 increased. If it didn't do that, if the CO2 increased in the past and the climate didn't change, then we would really have a cause for concern and could question, do we know what we're talking about? But the fact that it did in a scientific way, it's not proof for, but it's not negative proof, and that's what we want. Actually, what people have done, though, with the climate of the last 100 years, is they've run these climate models that understand the physics of the system, and if they put in things like volcanic eruptions, which cause a cooling, changes in solar activity, of course, when the sun's a little bit stronger, it gets a bit warmer, they can reproduce more or less what happened in the first half of the 20th century, but only by adding in carbon dioxide can they reproduce what's happened in the second half of the 20th century.
So that seems to be the nail in the coffin for carbon dioxide, because we've got a couple of emails here from people who are mentioning the volcanic eruptions. Simon Jennings says, I've heard it suggested the eruption of Krakatoa causes massive cooling of the Earth's atmosphere, and these effects are now diminishing. Could this be a contributory factor to global warming? And Brian, who's Brian Loveday in Cambridge, wrote to us and said, with so many active volcanoes around the world, how does the pollution from industry over the last 150 years compare with the number of things that have gone in the atmosphere because of volcanoes?
Right, well, the first question's easy. The aerosol, or the particles that go into the atmosphere from volcanoes do cause a cooling, but it only tends to last for a couple of years before the particles all drop out again back to the background level. So you'd have to have volcanoes going off all the time, really big volcanoes going off all the time into the upper atmosphere to have an effect like that. In fact, we do have our own kind of volcanic effect, because industry also puts sulfate aerosol, a little bit like the volcanic particles, into the atmosphere, and that is actually helping to keep us a little bit cooler than we would be otherwise. And so that's actually a concern. When we stop burning dirty coal, which produces sulfur dioxide, we'll actually make things a little bit worse for a while before they get better.
Jeff Kish says, and he writes to us, I know a lot of pretty smart people that think global warming is just part of a natural trend that humans have very little influence on. One person I know points to the fact that it's actually getting colder in the southern hemisphere, the Antarctic ice sheets thickening in places. How do you account for that?
Well, I'm afraid I can't even give you comfort there, although parts of the Antarctic haven't showed a very strong warming yet, mainly because they're so isolated from the rest of the atmosphere. The Antarctic Peninsula, for example, has been warming very fast. It's one of the places that's warming the most rapidly, and we now think that probably is related to global warming. We weren't really sure before, because we're cautious people, scientists, whatever people may think. So the rest of the Antarctic hasn't yet shown a very strong cooling, but the models suggest that it will. And it is actually true that the ice sheet under warming probably will get thicker at first, because what happens is around the edges where it's warmest, it will start to melt, but in the centre it's nowhere near the temperature where it will melt, so it won't start to melt in the centre, and you get a little bit more snowfall when it's warmer because you get more water vapour into the atmosphere, precisely what you were talking about. So that does make it a little thicker in the centre, a little thinner at the edges, but unfortunately all the predictions are that what happens at the edges wins.
The British Antarctic Survey's Eric Wolfe explaining to me how samples of the Earth's atmosphere trapped inside ice can give us clues to the planet's past climate. Now, one frequently asked question is, why did the carbon dioxide levels increase in the past whenever the Earth warmed up? Well, the details aren't certain, but scientists think that part of the story is that when the planet heats up, less carbon dioxide can dissolve in the oceans, so it comes out of the sea and remains in the air, where it can then act as a greenhouse gas and warm things up further. But putting its effects on temperature to one side for a moment, one undisputed effect of rising carbon dioxide levels is to make the ocean much more acidic. When CO2 dissolves in water, it produces carbonic acid, and this can attack calcium carbonate, which is the chemical that marine animals like mussels and oysters, and also corals, use to build their shells and skeletons. One man who's very concerned about the possible consequences is the marine biologist Frédéric Gazot.
The CO2 which is released by human activities such as the consumption of petrol, gas, coal, 1/3 of this CO2 is taken up by the ocean. So if you have more CO2 in the ocean, you will have stronger acidity. And the problem is that this acidity can threaten organisms which grow shells made of calcium carbonate.
And how do you know this has an impact on animals?
Well, I incubated in an aquarium, let's say, 2 populations of mussels and oysters. One population of mussel was incubated with a CO2 concentration, which is what we have now, and another population was incubated with increased CO2 concentrations in the water. And what I did is to measure the rate of production of their shells, and I saw that if you increase the CO2, you decrease the rate of shell formation.
Now, when you say you incubated them with increased CO2, how much increase? Is it within the realms of what we expect to see in the atmosphere within, say, the next 50 or 100 years?
Yes, I went further than these limits, but I covered the range which is expected in the next 100 years.
Now, obviously, the problem won't be confined just to shellfish, so what other animals might be affected?
A lot of different animals. For instance, the most famous ones, the coral reefs, are made of calcium carbonate. Also, you have really small planktonic organisms that we call pteropods. You have also coccolithophorids, which are really small planktonic algae in the ocean. And also you have species like sea urchins, for instance. And we have evidence for several of these species that if we increase the CO2 of the ocean, we will decrease their ability to produce their skeletons or their shells.
So irrespective of what CO2 actually does to the weather or to the temperature of the Earth, it will definitely have this effect on the oceans, and therefore there could be quite serious repercussions.
That's what we think, and that's what first experiments showed already. But now what we have to do is to see if these different organisms are able to genetically adapt to an increased CO2, and that's something which will be done in the next years, but we cannot really answer this question now.
So even if it didn't make a difference to global temperatures, rising CO2 could still spell disaster for the world's oceans. That was marine scientist Frédéric Gazot. He's from the Netherlands Institute of Ecology. But back on dry land, what other consequences could there be for a warmer world? Well, spare a thought for animals that use temperature to determine their sex, as Helen Scales from The Naked Scientist explains.
We thought that basically there are 2 ways that sex can be determined. So for humans and other mammals, as well as birds and some amphibians, an individual animal is a male or a female, depending on the sex chromosomes it inherits from its parents. So for us humans, females have 2 X chromosomes, and a male has one X and one Y. For other animals, sex is actually controlled without the help of sex chromosomes, but instead it's governed by temperature. So in some reptiles, like crocodiles and turtles, the number of male and females that hatch out of a clutch of eggs depends on the temperature that the eggs were kept at while they were being incubated. But now researchers from the Institute of Applied Ecology at the University of Canberra in Australia have discovered that one of their native lizards, the central bearded dragon lizard, not only have sex chromosomes, but they're also affected by temperature. So if you keep your eggs at a higher temperature, the ones that should be developing into males based on their chromosomes are actually turning into females. Now, the researchers think that the temperature is effectively switching off the effect of the male gene, the presence of which makes an individual a male, a bit like the Y chromosome. The whole chromosome in humans causes maleness to happen. And so it's by switching off this gene that we think the unborn lizards become female. Now, as well as rocking our understanding of how sex is determined, this latest piece of research might also have really important implications for the survival of these species in the face of climate change. Because if we have too many females being produced and not enough males for them to partner with, it can really spell serious problems for the survival of species. So an increasingly warm world could be an increasingly female world, at least as far as lizards go.
So a female-dominated world could have pros and cons. That was Helen Scales urging us to spare a thought for those animals whose sex is determined by temperature. So far, we've looked at the oceans and we've considered the consequences for some land animals of rising CO2 levels and increasing global temperatures. But what about plants? They thrive on increased carbon dioxide, don't they? Well, yes, but what that means is that they also use less water, which could mean more floods. Here's Richard Betts.
The question we're looking at is, does the direct effect of carbon dioxide on plants have any important effects on water resources and river flows in future projections of climate change? Because we know carbon dioxide is a greenhouse gas, and therefore increasing its concentration in the future will lead to climate change, and that will affect rainfall patterns and therefore water resources. But carbon dioxide also affects plants and their rate of evaporation. Plants remove water from the soil. They suck up water through their roots and essentially pump it back out to the atmosphere. This is a natural process, but this effect is slowed down by increased concentrations of carbon dioxide.
So wouldn't you expect the increased concentrations of carbon dioxide to make the plants all grow more? So although each plant might move slightly less water, there would be enough carbon dioxide to sustain a much more vigorous plant growth en masse, and therefore the total numbers would go up, not down.
You do expect that increased carbon dioxide concentrations would increase plant growth, but that doesn't completely offset the reduction in evaporation by the plants, so we still get an overall reduction in evaporation. I should probably explain how this reduction in evaporation occurs. Plants have tiny holes in their leaf surfaces, or under their leaf surfaces, called stomata, and they're kind of microscopic scale, so you can't actually see them with the naked eye. These holes allow carbon dioxide to pass into the leaf, so the plant can get hold of this carbon dioxide for photosynthesis.
And I suppose if levels of carbon dioxide are higher, then the plants don't need to open these stomata quite so much to get the same dose of carbon dioxide, and therefore they lose less water at the same time.
That's right. A lot of water is released by the plant leaves through these stomatal openings.
So what would be the consequence then if we do see an increase in CO2 and it means that plants respond in this way? What will happen to water all around the planet?
Well, if plants are extracting less water from the soil, more water will be left in the soil to drain into rivers, and therefore river flows would increase on average. Of course, river flows will also be changing as a result of climate change. They'll be increasing in some areas and decreasing in others. So where we're seeing increased river flows due to climate change, the increase will be even greater because of this effect of CO2 on plants. If river flows are decreasing because of climate change, because of reduced rainfall, the decrease would actually be smaller because of the effect of carbon dioxide on plants conserving more water. So therefore, although we may still get an increase in drought due to climate change, the increase may not be quite so severe.
How did you actually come to these conclusions?
We came to these conclusions using computer models of climate and vegetation and hydrology. They're actually the same kind of computer models that we use for weather forecasts, so they're tested every day. And these days we're quite happy to say we're not perfect, that the forecast is quite believable on the whole, so we know the models are doing the right kind of thing. But instead of running them for 5 days like you would for a weather forecast, we run them for 100 years and put in scenarios of increased carbon dioxide emissions or concentrations, for example.
And how high are you winding up those carbon dioxide levels to get the effects that you're predicting?
We're looking at a doubling of carbon dioxide concentrations relative to the pre-industrial state.
Is that realistic?
Yes, we'll achieve those levels probably in, say, 50 to 100 years' time, depending on exactly how much we continue to burn fossil fuels and how much we continue to deforest the world. But in the absence of any major actions to reduce carbon dioxide emissions, then yes, carbon dioxide concentrations are quite likely to double in the next century.
So a stormy forecast from climate researcher Richard Betts. He's at the Met Office in Exeter. Now, it's all very well producing evidence that rising carbon dioxide is a major climate catastrophe waiting to happen, but what can we do to remedy the situation? Well, there are two environmentally friendly solutions within easy reach, wind and wave power, and to tell us more about them, here's Ali Webb.
Wind energy was in the news late last year when the government approved a massive new offshore wind farm to be built just where the Thames empties into the sea. It's called the London Array, and it's going to have about 300 turbines generating 1,000 megawatts of clean electricity. That one wind farm will provide half as much energy as is currently operational in the whole of the UK, and enough to power about a quarter of the homes in Greater London. I asked the British Wind Energy Association's Alison Hill all about it.
The London Array offshore wind farm has certainly attracted a lot of attention. This is going to be the biggest offshore wind farm in the world by about a factor of 5. The UK is very firmly at the forefront of adopting the whole climate change issue and taking measures to secure future energy supplies. And wind farms are a good way of doing this.
OK, so are there any environmental costs to putting a huge wind farm offshore in the Thames estuary?
No technology comes without impacts. The London Array obviously has had several years' worth of very detailed environmental assessment carried out. And there will be consequences, it is inevitable, but this project has been designed as closely as possible to minimise those impacts. And we've just had reports published from the Danish offshore experience, which looks at 8 years' worth of environmental impacts from two of their offshore wind farms, which are currently the biggest in the world. And these demonstrate very clearly that wind farms do operate in harmony with the local environment.
Small wind turbines on people's roofs are a bit less visually impacting. I mean, do they work the same way as the large wind farms, and do you think they're feasible?
The principle of generating electricity from the wind is the same, whether you're doing it onshore, offshore, on a roof or on a pole down the back of the garden. What you will find with these smaller domestic scale turbines is that they're not necessarily as efficient as their commercial colleagues, the wind farm turbines. But studies have shown that you can see a reduction in your energy bills of up to a quarter in some cases. And possibly even more importantly, we found that where people have small wind turbines installed, they actually become more energy aware by seeing their meter ticking over when they generate electricity, but also ticking back when they use electricity. They become more conscious of how much they use. So they will switch lights off when they leave the room. They won't leave the TV on standby. And that actually is going to make a huge difference to reducing carbon dioxide emissions.
So putting small wind turbines up doesn't just contribute to your household electricity, but also changes your attitude.
That's possibly one of the most important points to consider about domestic or micro-generation technologies. They're something that we come into contact with in our daily lives and do actually change our daily routines for the better.
Brilliant. And my last question for you today is, would you, Alison Hill, live next to a wind farm?
I would love to live next to a wind farm. I really would. My parents in Scotland actually are in the process of buying a new house, and my mother was quite upset when they had to sell the old one because she had a beautiful view of a wind farm from her kitchen window. And she said she found it most soothing when she was doing the dishes. We actually have lots of people in the UK who deliberately buy houses that look out over wind farms. We've got farmers who use the wind turbines as weather markers for their projects. So yes, wind energy, I think, is a beautiful thing, and I would be delighted to live next to a wind farm. And there are many thousands, if not millions, of people out there in the UK who agree with me.
OK, so we've heard briefly about wind power, which is a pretty established technology these days that we're all pretty familiar with. But what's next in renewable technology? A company in Scotland called Ocean Power Delivery have come up with a very cool new machine which generates electricity by floating on top of the waves and which looks just like an enormous red worm. They built the world's first commercial wave farm, which was opened at the end of October just last year. It's off the coast of Portugal and it consists of 3 of these machines with the capacity to power a couple of thousand homes. I asked Ocean Power Delivery's Max Karkas how they work.
First of all, to describe what it looks like, if you imagine 4 train carriages out at sea, that's a bit what the machine looks like in terms of its shape and size. Now, the machine is moored at its nose, and what happens is that it points into the direction of the oncoming waves. It's free to swing and point into those waves. And waves travel down the length of the machine. And in doing so, each of these, if you imagine them as train carriages, articulates both up and down and side to side. And that movement's resisted by hydraulic rams, which are a bit like big bicycle pumps, which pump high-pressure hydraulic fluid through hydraulic motors which turn generators.
What environmental impacts could the machines have?
We certainly think that our footprint is very small. We have no fluids or greases in direct contact with seawater. We've got no rapidly moving pieces of equipment in the water. I mean, it's fair to say we're biased, of course, but we think our environmental impact is actually one of the least of any of the main power generating technologies.
What about the comparative costs?
That's absolutely right. The costs at this stage are higher, but that's because the technology is relatively immature. Like with all these technologies, you've got to produce something and get it out there in volume in order to drive the cost down. And what gives us tremendous hope is that our opening costs are substantially below where wind started 20, 25 years ago, and substantially below the current costs of solar photovoltaics. So all the projections are is that if we can really deliver into this market, then wave energy has the potential to become one of the cheapest costs of generation.
So why is it, do you think, that development of wave power is lagging so far behind the development of wind power?
Well, I think it's a mix of things. The challenges are threefold. They're technical, to make something that works reliably and can cope with the conditions. They're commercial, which is to find the right partners to work with. But also, importantly, they're political, because, what we're trying to do here is what any business school would tell you not to do, which is come up with a new product in what is, after all, a commodity market. Electricity is just a commodity, and what comes out of the socket, you can't really differentiate a bit between. People don't kind of brag about wave power electricity to their friends and enthuse about the electrons being made by artisan wave power engineers off the coast of Orkney. But so what's really required, and has always been the case in energy technologies, is a feeder market that can allow these things to go forward. And if we can do that, we can also build a major industry. If you look at wind turbines, it employs many tens of thousands of people worldwide, but sadly not so many in the UK, because we really missed the boat on that. So let's not miss it in wave energy.
So there are some promising alternatives to fossil fuels in the pipeline. That was Ali Webb talking with Max Carcass, and before him to Alison Hill. Well, that brings our review of the climate change situation to a close for now. I'm Chris Smith from thenakedscientist.com. Thank you for joining me, and enjoy the rest of your Christmas and a very happy New Year.